everyone, and welcome back to our NIRx webinar series on TMS fNIRS integration. If you joined us yesterday, you will remember we started with an inspiring talk by Professor Georg Kranz, who walked us through the principles of non-invasive brain stimulation techniques and how imaging can help map and optimize TMS effects. Today, we are continuing with the second part of the series titled iTBS and fNIRS integration from experiment to data preprocessing. We are happy to have with us Mrs. Minxia JIN and Mr. Weili and Ms, both PhD candidates from the Department of Rehabilitation Sciences at the Hong Kong Polytechnic University. In this session today, they will share their hands-on experience combining TMS and fNIRS, from designing experiments to tackling practical challenges in concurrent measurements, and finally to data preprocessing and early analysis steps. So if you've ever wondered what it really looks like to run a TMS fNIRS study in praxis, you are in for the right session. And as always, I'm joined by Cami, our wonderful marketing and events coordinator, who is helping me moderate today's webinar. If you're joining us and our webinar for the first time, welcome. Let me briefly introduce NIRx. For over 20 years, we've been manufacturing state-of-art fNIRS devices in Berlin and distribute them all around the world. At NIRx, we are dedicated to giving researchers the tools, knowledge, and support they need to explore the brain with confidence and creativity. We provide guidance and expertise to help scientists make the most of our technology, and we are always inspired by the innovative research being carried with our systems. And these webinars are part of our effort to share the latest and most exciting developments in fNIRS. You can connect with us anytime across our online platforms, and we are always happy to hear from you. And if you'd like to get in touch with us directly, just drop us a message at consulting@nirx.net. You can also subscribe to our newsletters. Simply scan this QR code on your screen or visit the link. There you will find the updates of our latest product features and releases. We usually send just a few updates per year. We are just keep it light. And before we begin, just a quick reminder of a few housekeeping points. Everyone is muted during this talk, but we encourage you to share your questions in the Zoom chat at any time. We'll gather them and address during the Q&A session at the end. And this webinar is being recorded, and the video will be available soon on our website and YouTube channel. And again, if you like to ask any further questions, you can always send us email at consulting or support@nirx.net. And now it's my pleasure to introduce our speakers today, Mrs. Minxia JIN and Mr. Weili and Ms. They're both PhD candidates at the Hong Kong Polytechnic University and working under the supervision of Professor Georg Kranz. Their research focuses on applying TMS in the context of depression, combined with advanced neuroimaging methods like fMRI or fNIRS. Mrs. JIN has authored nearly 20 peer-reviewed publications and investigates the acute hemodynamic effects of TMS in individuals with major depressive disorder. And Mr. Xia's work further explores the neurobiological mechanisms underlying depression and aims to optimize TMS treatment protocols. And we are very glad to have you both with us today. And Jimmy, I believe you start, and the stage is yours.
Hey.
Enjoy the webinar.
Thank you for your introduction. Let me share our screen first. 那我自己的话，这个。Hey, hello everyone, and thanks for having us here. I'm JIN Minxia, a PhD candidate, and today we are going to deliver the presentation on integration of simultaneous iTBS and fNIRS. We will share our experience based on collecting data from hundreds of cases, both healthy conditions or depression patients. And I will introduce the experiment implementation, and my colleague XIA Weili Adam, he will talk about the data preprocessing pipeline we are using currently. First, let me briefly introduce our study. We targeted the left dorsolateral prefrontal cortex using B65 coil, and the manufacturer is McVenture. So I'm gonna share the several steps we will do before data recording. The first step is TMS safety screening, of course. But this is actually the consensus in this field, so I will just skip it. And the second step involves TMS registration with or without individual structure MRI imaging. Registration with MRI image is good for precise targeting, but it's quite expensive for scanning each participant, so we do not do that in the current study. In this step, very important thing is to leave the space for fNIRS cap, because we have to wear the cap like here. In the conventional TMS studies, we just put the reference on the forehead. But in this study, we initially we put it on the facial, on our face. But due to the rich facial muscles, even a little expression can move the reference, so which may result in the registration inaccuracy. So we designed my colleague team and my supervisor, Dr. Kranz, they designed this reference holder, which is 3D printed, and it can firmly be put on the nose. But in our real experiment, we did not use this string because it is very uncomfortable, especially when the duration of the experiment exists for 30 minutes. So we just use tape to stick it on our nose, and it provides a very stable and reliable support for the reference. Okay. The step 3 involves measuring the resting motor threshold or acting motor threshold according to what you want to do. It is important to account for the increased distance between the coil and the scope due to the fNIRS octopus probes. We have two options for you to consider. One is to calculate the adjusted motor threshold using the equation established by Stokes. For their studies, they found that for each additional millimeter separating the coil and the scope surface, an additionally approximately 2.8% of absolute stimulator output was required to reach the motor threshold. For example, if we measure the MT from a motor cortex from a participant, and that is like 50% for this participant. But if we want to stimulate her DLPFC and with the fNIRS octopus between the coil and the scope, what is her adjusted motor threshold? According to the equation, it should be 50% plus 2.8% multiple distance of the stimulated site minus distance of the motor cortex. But as we assume that the distance of the scalp to DLPFC equals to the distance between the scalp to motor cortex, so the distance between these two sides should be the increased distance caused by the probe, so which is approximately the height of the probe, which should be 10 millicenter. So adjusted motor threshold for this case should be 50% plus 2.8% multiple 10. So that would be 78% for these patients. And we want to know how the adjusted motor threshold works. So we do the electric field simulation on some structure MRI collected from other projects. And the results demonstrated that the maximum electric field values are comparable between the adjusted motor threshold at 15 millimeter and with as the motor threshold at 4 millimeter. So it shows that the adjusted motor threshold works quite well, but actually the for quality will be reduced, of course, because the distance is increased. But if your coil is different from the Stokes studies, or if the coil with a different electric field depth for quality trade-off from Stokes study, I would recommend measuring the motor threshold directly with the cap and the probe holder, not with a probe on it. Just like the TMS EEG study, what they did in their study. Okay. Then we put on the fNIRS cap. Adam and I designed this customized montage to cover the bilateral prefrontal cortex. By saying customized, I mean we actually cut some new holes to make sure that each channel length is 3 centimeters for each cap size. And to localize the coordinates of each channels on the MNI standard brain template, we utilized a 3D digitizer for estimating the coordinates. And one thing we need to pay attention to at this step is that the probe used in this fNIRS system, in the Borealis system, actually lack the springs to secure probes firmly against the scalp, because we want to lower the height of the probe to increase the quality of the TMS-induced electrical field. So the signal quality is affected, particularly in area with more hair. So as a result, we did not use all the available probes to cover additional areas. So if you want to do this study using this system, you have to make a choice. You want to cover more area, but the signal will not be that good. Okay. To optimize the signal quality, we experimented several methods we use the bandage, like the figure 1, and the Q-tips on certain probes with poor connections. And ultimately, we found that using the tape, I don't know whether you can see it clearly. Using this tape, the white one, is the most effective solution. You can see the tape can firmly hold each optus in place and goes all the way down and secured by the chest band. The chest band is a very useful accessory which helps to stabilize the cap. In the experiment, we just gave it one more role to play. Okay, next. Next, different from the normal experiments, we will ask participants to lie down because we found this position can help them more relax and reduce movements. It is very important for our study. But we need to pay attention to that. We need to ensure that all participants maintain a similar posture, such as the recline degree, because some might argue that the blood flow speed might differently affected by different recline degree. And we would also ask participants to put their hands on their bellies and the legs relaxed. But no matter what posture you ask your participant to put, the most important point is to make consistent across participants. And step 7 involves positioning the coil with TMS navigation. In this step, we need to make sure minimal pressure to the probe, just like a little touch on the probe. Or we leave a gap between the coil and the probe, just like this figure. And this study is conducted by another colleague in our team, but using another fNIRS system. Because their probe, the height of their probe is much lower than ours. So they decide to, I don't know whether you can say it clearly, actually there is a plate with this kind of thing. We call it bridge. They use this bridge to separate the coil and the probe. So they can completely avoid the mechanical disturbance produced by the TMS during the stimulation. But in our study, because the probe height is much higher than theirs, so we did not use this bridge in our study. Okay. But regardless of your choice, keeping the head still is very important. So I would recommend a head holder. That might be a good option, but we do not have that one in our present study. Additional conditions for you to consider if you are trying to do concurrent TMS iTBS is that first one is the height of the probe. Which we measure to be approximately 11 millimeter, a little bit higher than 10 millimeter, because we know that a greater distance between the coil and the scope means the less for quality of the TMS-induced electric field distribution. You need to consider it when you design your study. Maybe do some electrical simulation to see whether the result, the intensity of the electrical field or the quality is satisfactory. And the second point is I would strongly recommend administering a single test train of iTBS. We do that in our study to assess individual tolerance to the stimulation-induced discomfort, particularly for those who are naive with DLPFC TMS, because we all know that DLPFC TMS is quite painful. It's much painful than stimulation on motor cortex. I remember a lady in my study, she even screamed when the first several pulses were delivered over her forehead. And I'm so sorry for that. And the data, of course, cannot be used. So after that, I will do this part for every single participant. Okay. And lastly, when using a TMS navigator to guide the coil position, it is very important to turn off the navigator camera before the data recording. Otherwise, the camera signal may interference with the Borealis fNIRS signal. In this test recording, we can see, please observe like this one, this channel, and this channel, and this channel. We can observe a sharp signal at like 0.4 Hertz. Initially, we were unsure of the cause, but after testing nearly all the light sources in the room, we determined that the interference is actually from the camera, which also uses near-infrared light. Therefore, I strongly recommend you to turn it off before the data recording, or you can cover the camera with a black visual hat, and that would be convenient for you to check the coil position after recording. This part, that's the end of my part. It's very simple. And thanks for your listening. If you have any question, you can leave it until the end of my colleague's part. I would be very happy to answer that. And now I will hand it over to the next part to introduce the data preprocessing pipeline.
Hello, everyone, and thank you for staying with us. My name is XIA Weili, and you can also call me Adam, and I will continue from my colleague's talk to present the second part of our presentation, the data preprocessing of our concurrent iTBS and fNIRS study. This section focuses on how we handled and cleaned the fNIRS signal collected during our simultaneous iTBS experiment. Okay, let's start. Okay, here is an overview of what I will cover today. I will start with some general information. Actually, my colleagues has already give you a lot, and I want to give you a sense of the experiment setup. This will help understand the pre-processing setups later. Then I will discuss some challenges we encountered when working with these types of data, especially in concurrent iTBS and fNIRS experiments. After that, I will walk you through our pre-processing pipeline. Before that, I want to say, please note, this is not a standard or universal protocol. It's simply the approach we found useful in our study. So we would like to be very happy to hear your opinions or suggestions for alternative or improved pipelines. Finally, I will show some results from each pre-processing step and a case study where we inject Botox into the forehead to reduce muscle twitching during stimulation, which one I will mention later. This serves as a clean comparison. At the end of this presentation, we will have some time for the question and answer. Okay, all the details about the experiment and the methodology, especially the data processing part, has been described in our previous publication, which you can see here. I give the reference here. And this is a figure that demonstrates the study design. Please let's focus on the upper right corner of the figure. In this study, the bilateral prefrontal cortex were monitored by fNIRS using this probe design. My colleague Jimmy has described it before, and the fNIRS signal in these regions was simultaneously recorded 3 minutes before, 3 minutes during, and 3 minutes after the iTBS. So we got 9 minutes continuous signal. When we looked into such 9 minutes continuous signals, there are many types of artifacts. Some are very common, such as the signal from the superficial tissues, like the skin or the muscles. or artifacts induced by the body movement, because you know if the experiment lasts for a long time, we cannot make sure the participant won't move at all. So such as additionally, even subtle motion such as deep breathing or swallowing can produce U-shaped or inverted U-shaped artifact. I put a figure here, the right up one. This figure shows how it looks like. This U-shaped signal changed slowly, so it's similar to the normal hemodynamic responses. So if we use the traditional ways, we cannot detect this artifact, such as we would like to use a spline or wavelet method. This method cannot detect this kind of motion artifact. On the other hand, in our concurrent iTBS and fNIRS setup, additional unique noises appear. For example, I think maybe the vibration of the TMS coil or forehead muscle twitches triggered by the stimulation, especially when we're targeting the TMS coil to the left DLPFC, will produce transient fluctuations in the fNIRS signals. I also put a figure here on the right lower one, which makes I also put a video here. I want to show the muscle twitch. Let's have a look.
2, 1. Okay, stop.
So every time the stimulation was given, the forehead muscle will twitch. We think this caused such kind of transient fluctuations. And this also makes the data difficult to interrupt because it happens at the same time of the TMS and where we are interested in.
2, 1.
Okay, to deal with these challenges, we developed a pre-processing pipeline using Homer 2 toolbox and our own MATLAB scripts. On the left side, you can see these steps are general in Homer 2, so I won't go into these steps here. On the right side, we did these steps using our own script, and the following slides will introduce each of these one in more detail. The main goal is to remove as many artifacts as possible while keeping the true hemodynamic signal. Okay, let's say them. I will introduce you one by one. The first step I said I want to introduce is a short separation channel regression. It says purpose here is to remove signals that come mainly from the superficial tissue I have mentioned, such as the skin and the muscle, and to minimize motion-related artifacts. A lot of previous studies have supported that short separation channel regression can achieve such objectives. We used a least square approach in our script to do this kind of regression, and we found the short channels that was most correlated with each long channel or the standard channels first, and used that as a regressor across the entire measurement sequence. As shown in this figure, the blue circles means the short distance channel. And you can also do this using the closest ones or averaging all short channels, depending on your interest or your citations, I think. And I won't go through the math here. The equation, I also put it here, the least square approach, because there is if you are interested in, there is a detailed explanation and video tutorial available at the link shown on this slide. It is provided by NIRx company, You can also download their script from their support center. And so they helped us a lot in our study. Anyway, this step help us isolate cortical signals by filtering out superficial components. Next, we applied PCA and ICA. The idea is to remove the noise component, for example, the U-shaped or inverted U-shaped component and the transient fluctuations you saw earlier. Why we choose PCA and ICA rather than other traditional ways? Because as I mentioned, the U-shaped one is quite difficult to be automatically detected by the traditional ways, and the transient fluctuations always combined by spiking and shifting, so it's also very hard to be cracked. So we used the PCA to reduce data dimensionality while preserving at least 99% of the total variance. Then we used fast ICA to separate the signal into independent components. We select the components for removal based on 3 criteria: their temporal pattern, their spatial distribution, and their power spectrum, because we don't want to remove any meaningful signals. For example, here are 2 examples. The first one is a U-shaped or inverted U-shaped component. Its time series exhibits a long temporal range, like around 40 to 60 seconds. A U-shaped or inverted U-shaped spiking during the, it usually happens during the resting period, and it also usually occurs in the bilateral marginal channels, as shown in the upper part of the figure. And the power spectrum of it looks like this one in the figure, the upper middle one. In the case of transient fluctuations, its time series displayed multiple peaks and shifts I've mentioned within a short temporal range, aligning with each 2 seconds of iTBS stimulation. So we think it's an artifact because normal hemodynamic response cannot change so quick as the stimulation was given. And it usually occurs in channel located on the stimulated hemisphere. This combination helps us identify and remove non-neural components effectively. After ICA, we apply wavelet filtering to remove any residual spikes or artifacts that might remain. We called Homer 2's wavelet function with an alpha value of 0.1. Finally, we applied a high-pass filter with a cutoff frequency of 0.09 Hz. These steps, we did these steps because we want to remove high-frequency physiological noise, but still keeping the overall trend of the signal intact, because we have a long time of signal. I mean, we have a 9 minutes of signal. We want to see how the hemodynamic changed during the whole 9 minutes. You can also use bandpass filter as a traditional way. It's depending on your interests or study designs. A key point here, a tips or a warning here, I think. We must be very careful not to overclean the data. It's because when we run in the ICA, before we did the analyze regularly, it's easy to remove too much and accidentally eliminate meaningful neural signals, especially in the ICA step. To better understand what, on the other hand, to better understand what clean data should look like, we run case study. Our participant actually, he's our supervisor, and received Botox injection into his forehead to reduce or even eliminate the muscle twitching caused by TMS. Here's a short video showing the difference before and after the injection. Let's have a look.
Another one?
And this is the after the video took when he received the Botox injection. So you can see there is no muscle twitching anymore when receiving the iTBS at the same target site and the same intensity. This gives us a useful reference for exploring what a true or artifact-free signal might look like during iTBS. Here you can see I would like to show you some results from the stimulated left DLPF channel. It's channel 10, and the figures shows the HBO here before and after each pre-processing step, each row of the figure. For example, the first row is the raw data, and the second row is the signal after doing the short separation channel regression. And the third one is after ICA, and the last one is after wave rate filtering. Sorry, the figure is very small because I want to put them together to let you have a direct comparison. And also the before and after Botox injection comparison. Here, the left and the right figure. Notice that before Botox, the raw data contains strong artifact from forehead muscle twitching, or maybe coil vibration. I will give you an answer after this slide. Even after short separation channel regression, you can still see the this kind of artifact. But after applying our pre-processing pipeline, especially after the ICA step, most of these artifacts were greatly reduced. You can see from the third row, I think. There is no such kind of artifact anymore. And now we look at the right side, the right figure. After Botox injection, no such kind of artifact anymore. So the Botox injection works well. So I think we did not remove any. After Botox injection, during the data pre-processing, we did not remove any components at the ICA step when we were handling. So it also proves that muscle twitching cause much stronger artifacts than coil vibration. I think because Botox injection cannot prevent coil vibration, and we put the coil at the same position. So I think coil vibration is not a problem when compared with the muscle twitching. Now we look back to the left figure. The final cleaned signal looks quite similar to the Botox data. Of course, this observation is still based on visual inspection, but it suggests our pipeline is effective. This slide shows a HBR of the same channel. It also works well, as I said in the last slide. I think we can have a quickly look. Okay, on this slide, I would like to show you the signal from the contralateral DLPF channel. This is a HBO signal. Interestingly, these channels were much less affected by artifacts to begin with, even before Botox injection. injection. So we think we use the criteria to choose ICA depending on where the artifacts come from. It works. After pre-processing, the cleaned signal again resembles those recorded after Botox. This consistency further supports that our pipeline can effectively suppress non-neuron artifact while preserving the underlying hemodynamic response. Again, these are visual observations, and the more quantitative validation will be our next step. And this is the HBR of the same from the same channel. Okay, here comes to the end of today's presentation. We would like to say thank you to our supervisor, Professor Georg Krantz, as well as all our teammates, friends, and family for their support. Thank you all for your attention, and we are very happy to take your questions or hear your thoughts about our presentation. Thank you very much.
Thank you so much. I think that was a wonderful presentation and amazing studies that you did. We are having couple of questions. Just to briefly comment before we start with the Q&A session. It's really amazing how data look like, even with all type of noises that TMS itself produces, like all type of artifacts. We know it a lot from EEG, from fMRI studies. The TMS responses, they're very complex in terms of the brain activation, in terms of physiology activation. And it is wonderful to see how fNIRS data, even though containing all those type of noises, look like, especially comparing to EEG. So it is very exciting to see all type of results that we can get with it. And with that, let us move to the question sections. We had one question from the registration form, and the question was, what do you see as the future of iTBS fNIRS integration in terms of real-time integration? Do you see any potential for the real-time application? You're muted.
Thanks for this question. Actually, what we are doing is using iTBS fNIRS to do the real-time recording. What we are doing is to using this combination to investigate how our brain reacted during the stimulation, and how the signal affected by personalities or age, gender, or that kind of thing. So maybe this kind of research can guide us to optimize TMS treatment, especially on the DLPFC. You can see detail in the publication we've shown in Adam's slides, which is published in Brain Stimulation. And what we also doing is we use iTBS and fNIRS to see the acute hemodynamic responses in depressed patients, and how it is different from healthy people. And if these responses can be used as a biomarker for iTBS treatment response, or can this response can predict future illness development. But we only have very initial result of this part, so I cannot see that a lot. So I think this integration will be good as a biomarker, but if you want to use that to deeply investigate TMS mechanism, I don't think it will work well. Yeah. Have anything to? No. Oh. Yeah, then
Okay.
that's it.
Thank you. Thanks. And then maybe we can dig in. We have more practical questions about the data analysis. The question from Armin. Maybe Armin, if you want, you can unmute yourself and ask them in person.
Could you please elaborate on this selection of XIA components?
Oh, okay, I will answer this question. After we run the fast XIA, we can usually get maybe around 20 components, or it depends. Then we will check, because we will say MATLAB give us the components, how it looks like and where it happens, and the power spectrum. So I will get 20 figures of that. So I will check one by one to see which one fulfill all the criteria. Then I will pick this one to be removed, or then keep others. Then after that, I will get I think I will get a cleaner one with removing the artifact we don't want to have. And the criteria, I have introduced it in our slide. We learn it. We also, I think we also, I mean, someone who are studying EEG suggest us to do that, because in EEG studies, they will pick the components depending on these criteria to make sure not remove. We won't remove useful or meaningful signals. And then the second question is the order of the pre-processing steps. Yes, I think it's a good question, because when we are developing our pipelines, I also think about that, especially the short regression channel, because short channel separation channel regression step, because in other studies, not other studies, sorry, in other toolboxes, like such as, for example, Homer 2, they usually apply the short separation channel at the last step. And so at that time, I also have these questions. I remember that I also asked someone maybe from your company about that, and he or she, I forgot, sorry, said it's also hard to say, because we cannot find such kind of evidence to say which step should be the first one or which step should be the last one. But I also ask this question to one of my friends who has his major in math. He said if the equation or the function you use at each step is for example linear regression, or we want to change it, so we will sorry, I'm not good at math, so we won't change the result, I think.
Yeah,
Do you
thanks so much.
understand me?
Thanks so much for getting back. I just wanted to understand first for the XIA if it was more like an automatic procedure, so like a objective procedure, or is more like subjective driven, which is of course a very important question. The second, about the order of pre-processing steps, is of course a very broad question, and you're fully correct. I also learned over the years that sometimes it might also be interesting to basically change the order around, at least to some extent, to see if you can get the same effects out with different orders, to see if even different pre-processing pipelines or orders of pre-processing pipelines might bring you to the same result, to see if there's not a specific artifact within the specific combination of your pre-processing steps. So it was just, but it's very hard to answer, because it very much depends on the reliability of your final measure in the end, right? Because what do you compare in the end as the measure of success of your study? So that means in the best case, you slightly adapt your order and you find the same, at least qualitative pattern, but best also the same quantitative measure. So, but it's a very complex question in the end. So thanks for answering. Can I ask a third question? Because I'm just thinking about it. Because I just want to understand for myself. Because in the beginning you mentioned the position of the subject, and the subject was lying down, right? Is it correct?
Yes.
So I was wondering, because I think it's known that the response in the fNIRS signal in HBO and HBR changes according to the position of the subject. So there's multiple effects, gravity, for instance, but also the pooling of blood when the body is lying down and the head is lying down. So is it necessary? So just my stupid understanding, but is it necessary to have this position lying down, or could you also do the same measurements with the subject in an upright position? Because, for instance, one thing I keep in the head of my mind is how does the baseline change in these lying down positions? So if the baseline changes relatively and is increased, of course, any effect will be harder to detect because the baseline is relatively elevated. So I was wondering if you check these effects also in an upright position, or if the subject have to lie down, there's no other way to do it. So it's like a practical limitation. It's just my stupid.
No, it's a very good question. So I would say it's not necessary to let the participants lie down, but according to our experience, if the students sit up, it is very, very, very hard for them to keep the head unmoved during the whole 9 minutes. So even if we are not sure whether the the live posture will affect the HBR or H3O signal, we choose that method to make our participants more comfortable, and it will make the whole procedure more feasible. But I think that your question is a very good question. Maybe in the future we can do like a cross-sectional, not cross-sectional, a crossover study to see how the posture change the HBR or HBR signal. But now I cannot tell you how it affects. Sorry, that's a very good question.
Thanks for answering. Thank you. Thanks so much.
All right, thank you. And then we have another question about the neuronavigation. So thank you so much. Very informative presentation. I have a question regarding the neuronavigation camera. Indeed, if the camera is on, it might interfere with fNIRS. But if it's turned off, how can we assure TMS is still in the target? Because we still have minor head movements, and they are cumulative in time. Would you have any recommendations for that? Again, thank you so much.
Thank you for this question. I also have this wondering during the experiment, but we have to protect our signal quality, so we have to make a choice. What I did is I will put the black cap on the camera. I will not turn it off, but for Adam, he will turn it off in his studies. But another thing I would do is I will take photos from different perspectives during the study at the beginning and after the stimulation to see whether he or she changed a lot. And then I will also, after the recording completion, I will remove the cap to see whether the patients moved a lot. I think we set up a criteria. If the patients move a lot, I mean beyond your criteria, you can reconsider whether the data is used or not. So this is our experience, and our experience is that most of the patients will not move their head during the whole process. So, even if the camera is on and you saw the participants moved a lot, then the data cannot be used anyway, right? So the TMS camera on or off actually doesn't matter. You just need to find
thank you so.
Yeah.
Thank you so much. Just one question about this. Could you please tell which brand of camera you're using? Because as far as I know, this interference happens just because the overlapping wavelengths. Neuronavigation cameras, some of them operate at the similar wavelengths as fNIRS systems, so that's why we see this interference. But it's not happening with all the neural navigation manufacturer. So could you please tell which brand you're using?
The one we used is Localite from Localite company. And also I have a suggestion for the last question, who asked the last question. If you really want to check whether the coil or the patient moved, the participant moved or not, I think in our way, we try to block the camera, whether turn it off or with a black shower cap. I think you can put a shower cap, maybe a shower cap on the head of the participant. So that the upload can be blocked, but actually we also try this way. Maybe because the quality of the cap is not good enough, the signal still was still affected by the camera. But if you can find a good cap or some other caps that can totally block the near infrared light, then I think it will work. But you should make sure not to cover the reference as well. So this is my suggestion. Or maybe in NIRx company, you can also develop such kind of cap to help us who are doing such concurrent TMS and fNIRS study. Thank you.
Thank you. So from our experience, we do see some interference, of course, wherever, as I mentioned, the wavelengths are in the same range. So usually our recommendation would be to block the interference, either to put on the shower cap, the black one that blocks the light, or if it doesn't help, we also recommend to put some foil, aluminum foil inside, which we are sure that it blocks it for sure. So that would be, but that's a very important point. Thanks you for bringing it up. Whoever wants to try TMS fNIRS study, be careful with the camera interference indeed. Yes, so do we have any, we ran out of time almost. If someone has any further questions, please feel free to write us. And we will be happy to follow up. And with that, I think we can finish. Thank you so much again, Jim and Adam. It was great to have you with us. And yeah, thank you so much.
Bye-bye.
Bye.